Hello and welcome to my video tutorial on fundamental counting principles. In this video I would like to talk about the fundamental counting rule, and then from there I'd like to talk about another counting technique called permutations, and then from there I would like to talk about another counting technique called combinations, and then at the very end I would like to discuss how to compute probabilities using these fundamental counting rules. So to get started with the fundamental counting rule, a few weeks ago, 6 of us got together and went to the 5280 Denver Dining, and the menu was presented to us, and on this menu we had an appetizer component that we were allowed to have, and then we had an entree component, and then at the very end of our meal we had a dessert choice that we could choose from. In the appetizers, there were 5 appetizers that I had to choose from, and in the entree there were 3 entrees that we had to choose from, and in the dessert category there were 4 options that we had to choose from. So now the question is how many ways could I have picked a meal? So the fundamental counting rule over here says that in a sequence of n events, so I have these 3 events. I have the appetizer event, the entree event, and the dessert event, in which if each event has these k different choices, so k1 goes to the first event, k2 goes to the second event, and k3 goes to the third event. So in this case, this is k1, this is k2, and this is K3. Then the total number of possibilities is just a product of all these number of choices within each event. So to determine how many meals that I had, I just take the product 5 times 3 times 4, which is equal to 60. So there were 60 ways that I could have constructed a meal based on the appetizer, entree, and desserts. So another example using the fundamental counting technique then is, suppose that you go to your favorite store and they're having a sale on coats, probably since the end of the summer, and getting rid of some coats. So you go up to the coat rack and you happen to notice that there are different sizes, and you also happen to know that there are different colors. So now the question is how many ways do you have to pick a coat? So suppose that the sizes that you notice are small, medium, large, and extra large. So that means there are 4 sizes to choose from, and the colors, suppose that there was red, white, and blue. So that means there are 3 colors to choose from. So now the question is how many ways do you have to choose a coat? So again, using the fundamental counting rule, we take our size choice, and here we can see that there is 4, and here we have a color choice, and there's 3. Multiplying these 2 together, we can see that we have a total of 12 ways to pick a jacket. So another important rule that we have, or mathematical operation that we have, is a factorial. So this is n factorial. So n factorial is just defined to be the product of n times n minus 1 times n minus 2 all the way down to 3, 2, and 1. So for example, 5 factorial is equal to 5 times 4 times 3 times 2 times 1, and note that 5 times 4 is 20, 20 times 3 is 60, 60 times 2 is 120, 120 times 1 is 120. So that's how we compute factorials, and I should state that n is always an integer. And by definition, 0 factorial is 1. So factorials can get pretty big. I mean, when you start getting up to 15 and 20 factorial, to multiply 20 numbers or 15 numbers together gets pretty big, but there is a way that we can have technology assist us in this computation. So on our calculator, we can compute, for example, 10 factorial by entering 10, and then come over here to the math button, and then arrow over here to the PRB button, and notice that menu option 4 has the factorial button. So 10 factorial, and then compute that, and notice that there it is, 3,628,800. So factorials are easily computed using our technology as well. So the next counting technique I would like to take a look at is what we call a permutation. So a permutation is computed by using this formula here. This is one of the formulas that we are going to take a look at. But to motivate the idea of exactly what a permutation is, a permutation is the total number of arrangements where order matters. So the idea is, let's just consider that we are going to hang 4 pictures in a room. So if this is our room, and if we consider pictures A, B, C, and D, then one thing I can do is I can take and hang picture A right here. I could take picture B and hang picture B right here, take picture C and hang it right here, and take picture D and hang it right here. So one arrangement of hanging these pictures is A, B, C, and D. Or another arrangement is going to be, I can hang picture C right here on this wall, I can hang picture A on this wall, I can hang picture D on this wall, and then I can hang picture B on this wall. So that my arrangement now is C, A, D, B. So notice that hanging the pictures in this arrangement and hanging the pictures in this arrangement are different. So and this is the case where we say order matters. So now the question is if I have these 4 pictures and I want to hang all these pictures on the 4 walls, how many ways are there to do this? Well, here we have to recognize one main fact, and that is order matters. Since order matters, we know that this is going to be a permutation. Since we have 7 objects, since I have 4 objects and I want to hang up these 4 objects on these 4 walls and I'm going to use all 4 of them, then that means there is 4 factorial ways to do this. So 4 factorial then is equal to 4 times 3 times 2 times 1, which is 4 times 3 is 12 times 2 is 24. So there are 24 distinct arrangements that I could take these 4 pictures and hang these up on these 4 walls. Another interesting one is taking a regular deck of cards and shuffling a deck of cards. So here we have to remember that when we take a deck of cards and we shuffle the deck of cards, order matters. So each arrangement is different. Since I have 52 cards and I'm going to use all 52 cards to shuffle a deck of cards, then that means that there is 52 factorial ways to shuffle a deck of cards. And again, 52 factorial is pretty large, so let's go 52, math, PRB, menu option 4. And notice that when we enter this number, be careful when you take a look, this says E67. So let's just remember that E67 is scientific notation, so that means we take the decimal, move it to the right 67 spaces. So I think we can all agree that there is a large number of ways that we can shuffle a deck of cards. So the next topic in permutations I would like to take a look at is, suppose that there are 21 people in a classroom and 3 officers, that is a president, a vice president, and a treasurer, are to be chosen. How many ways can these officers be filled? So again, we have to ask ourselves, does order matter? Again, on these types of questions, that is the first question you want to ask yourself. So in order to determine if orders matters, so for president, if I chose Tim, for the VP I chose Sally, and for the treasurer I chose John, is that the same as choosing Sally for the president, John for the vice president, and Tim for the treasurer? So I think we can agree that these two arrangements are not the same, so we can conclude that order matters. So now the question is out of a pool of 21 people, we want to fill 3 spots or 3 places, and so we want to know how many ways can these officers be filled. So a permutation on n objects taken r at a time, okay, is computed by this formula right here, n factorial divided by n minus r factorial. So keeping that in mind, remember we said that n is equal to 21 and r is equal to 3. So now all we have to do is substitute into this formula. So here we get 21 factorial divided by 21 minus 3 factorial. So this is equal to 21 factorial divided by, so 18 factorial. So to compute this, note that all we have to do is note that 21 is 21 times 20 times 19 times 18 factorial divided by 18 factorial. So this cancels with this, so I end up with 21 times 20 times 19, and when I compute that, so 21 times 20 times 19, just a little side view here, this is all I did was entered this in, press enter, so we get 7,980. So this is the number of ways that I can fill for a president, a vice president, and a treasurer back here out of 21 people. The calculator also has a built-in routine as well to compute this formula here, 21p3. We can note that all we have to do here using the calculator is to enter 21 and then go math, again back to our PRB, and then notice that menu option 2 is NPR, and then enter 3 and then press enter, and note that the calculator will also compute this for us as well. So that's a handy little tool. Next example, suppose that a 30-member debate team needs to choose a main speaker, an assistant, a researcher, and a presenter. How many ways can this be done? Again, we have a pool of people and we are filling specific slots. So when we are filling specific slots, we know that order matters. So in this case, we have a pool of n equals 30, and we want a main speaker 1, an assistant 2, a researcher 3, and a presenter 4, so R is equal to 4. Since we're filling these specific slots, we know that order matters, so the number of ways that this can be done is a permutation, so this is 30 permuted with 4. So again, to compute this, we just go 30 math PRB for NPR, menu option 2, and then 4 and press enter. So we get 657,720. So that's the number of ways that from 30 people that we can fill these 4 slots. So now let's take a look and go back to our picture example. Again, I'm using the fact that we have picture A, B, C, D. But now you own these famous pictures, but now a museum, say for example the Denver Art Museum, wants to borrow any 2 of these pictures. Now again, since they just want any 2 of these pictures, let's take a look at how this can be done. So if you choose picture A, then that means that we have picture B, C, and D. So that means we have picture AB, picture AC, and picture AD. If we went with picture B, then we have A, C, and D. So that means we have the arrangement BA, BC, BD. If I chose picture C first, then I have A, B, D. So that means I have the arrangement CA, CB, CD. And if I chose picture D, then I have A, B, and C. So that means I have arrangement DA, DB, and DC. But let's also note that since they're just wanting any 2 of these pictures, that the arrangement of AB is the same as the arrangement BA, because they're just wanting any 2, so I can get rid of this arrangement right here. And AC is the same as CA, so I can get rid of that arrangement. And arrangement AD is the same as DA, so I can get rid of that arrangement. Arrangement BC is the same as CB, so I can get rid of that. And arrangement BD is the same as DB, so I can get rid of that arrangement. And CD is the same as DC, so I can get rid of that arrangement. So that leaves me finally with 1, 2, 3, 4, 5, 6 distinct arrangements here. All right? So notice that in this case, the ordering did not matter. So when the ordering does not matter, this is what we call a combination. So the number of combinations of n distinct objects taken are at a time without repetition, where order matters. We'll throw that up here. Then is given by, so this is just some symbol notation here. The most popular ones are these 2 right here, where this is n choose r, or if you've taken a college algebra course and they've talked about the binomial coefficient, this is read n choose r. So the computation then is n factorial, r factorial, and minus r factorial. So again, when order does not matter, order does not matter, then we use a combination. So again, if I have 4 pictures, so n is equal to 4, and the museum wants any 2 of those, again, we're not filling any specific slots. We don't care how we get these 2 pictures, just as long as we get these 2 pictures. So I also like to use the analogy of playing poker. So for those of you that are interested in playing poker, if you're up there at Central City playing poker, and you're dealt your 5 cards, and you pick them up and you look at them, and you happen to notice that you have an ace, king, queen, jack, 10 of diamonds, then you notice that you have a royal flush, which is the highest hand in poker. So now my question to you is this: does it matter how you got those 5 cards, or are you happy that you just got them? And I think most of us will agree that we are just happy that we got those 5 cards, and we don't care what order that we got them in, because a royal flush is still a royal flush. Or for those of you that like to play the Colorado State Lottery, you have your 6 numbers, and on Wednesday or Saturday when they do the drawing of the numbers, does it matter what order the numbers come out, the ping pong balls of numbers? Does it matter what order that these numbers come out, or are you just happy that your 6 numbers and the 6 numbers that were chosen just happen to be the same? And I think we'll all agree that we're just going to be happy that they're all the same. So that means that order does not matter. So in this case then, plugging into the formula, we have 4 factorial divided by r factorial 4 minus 2 factorial. So we have 4 factorial, 2 factorial, 2 factorial. So we have 4 times 3 times 2 times 1, 2 times 1 times 2 times 1. And this 2 times 1 cancels with this 2 times 1. And 2 times 1 is 2, so 2 goes into 4 twice. So notice what we're left with is 3 times 2, which is equal to 6, which is what we came up with earlier. So again, combinations are used when order does not matter, or you're not filling any specific slots. So if a classroom contains 21 people and a 3-person committee is to be chosen, how many ways can this be done? So again, we have a pool of 21 people, so n is 21, and we want 3-person committee. So here r is equal to 3. So now the question is does it matter how I get these 3 people? So since an arbitrary committee of 3 people is to be formed, and they're not filling specific slots, we can then conclude that this is going to be a combination. So we can use the, sorry, that should have been 21. We could use the 21 choose 3 formula. So rather than doing this one by hand, let's take a look at how we can use our technology to assist us. So the 21 choose 3, again, we'll go 21, and then we go math, and then over here to the PRB, and notice menu option 3 is NCR, and now we can put a 3 in here and press enter, and notice that there is 1,330 ways to do this. So for my next example, I would like to take a look at a company has 7 senior officers and 5 junior officers. An ad hoc legislative committee is to be formed. How many ways can a 4-officer committee be formed if, and now we have each one of these. So again, we have to note that we have 7 seniors and 5 junior officers for a grand total of 12 officers altogether, and we want a 4-officer committee. Now again, since this committee, we are not told that any specific slots are being filled, we know that this is going to, that the order is not going to matter. So that being the case, I want to choose any 4 officers. So here we're not specified which type of officers, so we just take a look at the pool of officers. So in this case we have 12 officers, and I want any 4 of those 12. Since order doesn't matter, I know that there is going to be 12 choose 4 ways of picking these officers. So then again I can come over here and go 12 math PRB and menu option 3, enter in a 4, and I have that this is equal to 495. Yeah. So the next one is I want 4 senior officers. So again, I have to ask myself, how many senior officers do I have? Well, clearly I have 7 senior officers. How many of these senior officers do I want? I want 4 of them. Does it matter how I get these 4? And the answer is no. So I know that this is going to be a combination. So there are 7 choose 4 ways to do this one. So again, I can compute 7 choose 4 by going 7 math PRB menu option 3 and then enter in a 4, press enter. So here I have that there are 35 ways, 35 different arrangements to do that. So the next one says that I want 3 senior and 1 junior. So this is going to be the important part here. So the idea using our fundamental counting principle says I need to pick seniors and then I need to pick a junior. Okay, so how many seniors do I have? I have 7 senior officers. How many of those 7 seniors do I want? 3. Does it matter how I get them? No. So order does not matter, so there are 7 choose 3 ways to do that. And junior officers, I have to ask myself, how many junior officers are there? There are 5 junior officers. How many of them do I want? Well, I need 1. Does it matter how I get them? And the answer is no. So there is 5 choose 1 ways of doing that. And then I'm going to product these together. Okay, so now using my calculator, I'm going to go open bracket first, then I'm going to go 7 math PRB menu option 3, and then choose the number 3, close bracket, open bracket 5 math PRB menu option 3, 1, close bracket, enter. So this will compute all of that stuff and product at the same time. So here our answer is there are 175 ways that I can do this ordering. So the next one is we want 2 senior and 2 junior. So again, since I'm separated with these and conjunction, I know I'm going to use my fundamental counting principle. So again, I'm going to go senior, junior, and then again I'm going to ask myself, how many senior officers do we have? 7. How many do I want? 2. Does it matter how I get them? No. So this is a combination. How many junior officers do we have? 5. How many do I want? 2. Does it matter how I get them? No. So order doesn't matter, so there's 5 choose 2 ways of doing that. And again, I just multiply these 2 together. So coming over here, open bracket, 7 math PRB menu option 3, 2, close, open bracket, 5 math PRB menu option 3, and then enter in a 2, close, press enter, and there are 210 arrangements to do that. So now we have to take a look at least 2 senior officers. So I'm going to clear this real quick. So what does it mean for 2 senior officers? At least 2 senior officers. Well, that means we can have 2 senior, 2 juniors, or we can have 3 senior, 1 junior, or 4 senior, 0 juniors. Okay? So that means we can have 2 seniors and 2 juniors, or 3 seniors and 1 junior, or 4 seniors and 0 juniors. So again, the idea is everywhere you see an and, you multiply, and everywhere you see an or, we will add. So again, we want to take a look first at this guy. So 2 seniors, 2 juniors. So again, same process. How many times, or how many seniors do we have? 7. How many do I want? 2. Does order matter? No. So there are 7 choose 2 ways. And for the juniors, well, we already know that this is going to be 5 choose 2. Or, so I have to add 3 seniors, 1 junior. So again, how many seniors do we have? 7. How many do we want? 3. Does order matter? No. So there's 7 choose 3, and for the juniors, 5 choose 1. Or there's 4 senior, 0 juniors, so we already know that that's going to be 7 choose 4 from some previous work. And again, we can have the calculator do all of this for us. So we can just go 7 choose 2, 7 math PRB, menu option 3, 7 choose 2, 5 math PRB, 3, 2, close, plus, open bracket, 7 math PRB 3, close, and then 5 choose 1, so that's 5 math PRB, menu option 3, and a 1, close, plus 7 math PRB, menu option 3, 4. And then press enter. Oops. Oh, I forgot to put my number in here. So that's 7 choose 3, second insert 3. Okay, that should work. So that's equal to 420. So I hope that these exercises and examples and discussion helps on using the fundamental counting principle, also helps using the counting technique of permutations, and also helps to use the counting techniques using combinations. So next on our list is to compute probabilities using our fundamental counting rules. So let's take a look at the example that we have at hand, this very first one. It says, find the probability of getting 4 aces when 5 cards are drawn from an ordinary deck of cards. So we are going to use the formula that we learned back in chapter 4, that the probability of an event is equal to the number of ways that the event can occur divided by all possible outcomes. So in this case, this example says that we're going to be dealt a deck, or I'm sorry, we're going to be dealt a 5-card hand from a standard playing deck of 52 cards. So the outcome here is getting 4 aces, and then we need one other card that just remains. So we have to come up with, how do we get 4 aces, and then how do we get that extra card? So all we have to do is ask ourselves, how many aces are in a deck of cards? We know that there are 4 aces in a deck of cards, and how many of those aces do we want to get? Well, we want to get all 4 of them. And then the next thing we want to ask ourselves is, does the order matter in how we get these aces? And the answer is no. So that means that there is 4 choose 4 ways of getting an ace, which is going to equal to 1. And then we have one other card remaining. So since there's 52 cards in a deck, we've already got the 4 aces. So how many cards are remaining in the pool of cards that is available to us? and I think we can all agree that there are 48 cards. Since we have the aces, we remove all of those, so that remains 48 cards. Alright, so 48 cards, and how many of these do I need? Well, I only need one card left, so there are 48 choose one ways of getting that last remaining card, since order doesn't matter. So that takes care of the top part here. And now the question is all the possible outcomes of the sample space. So in this case, since we're being dealt 5 cards from an ordinary deck of cards, we know that there are 52 cards in a deck of cards, and we are only wanting 5 of those cards. And then the next question is does order matter? And the answer to that question is no, order does not matter, because we don't care how we're getting this 4 aces, and we don't care how we get the additional card. So this is divided by 52 choose 5. In fact, with cards and being dealt 5 cards, that's always going to be our denominator. So 4 choose 4, how many ways are there to choose 4 aces from 4 aces? Well, there's only one way to do that. And I want 1 card from 48 cards, so I just want to pick one of those cards. So 48 choose 1 is just 48, divided by 52 choose 5. So using the calculator, we can plug this in. So the numerator, again, we can just go, if you want to see this in its brute force, we can go 4, oops, I need to go open bracket, 4 math PRB menu option 3 4 close times 48 math PRB menu option 3 1 divided by open bracket 52 math PRB menu option 3 choose 5. Press enter, and notice that with this E, notice when you see this, means we got to take the decimal place and move it 5 places to the left. So there's 1, so that means there's 4 zeros, so 0.00002. So that is the probability of getting 4 aces out of 5 cards. So in other words, this question is asking, if you're playing poker, what is the probability you will get a 4 of a kind? So all I have to do now is to note how many different kind of cards, and then I can multiply this by 13, because there are 13 different ways to get 4 of a kind. Okay? Alright, this next one is a popular question. A box contains 24 transistors, 4 of which are defective. And if 4 are sold at random, we want to compute these following probabilities. Okay, so we're going to select 4, and we have a pool of 24. So again, using the fact that we have the number of ways an event can occur divided by all possible outcomes, again, all possible outcomes is going to be n choose however many you're going to get. So in this case, our denominator for each one of these is always going to be 24 choose 4. So let's take a look. Exactly 2 are defective. So if we want to pool it, go in and grab 2 defective, we have to ask ourselves how many transistors are defective. Okay, so we know that 4 are defective, and we have 2 of them that are defective. So since we have 4 bad ones and we want any 2 transistors, and order doesn't matter, so there is 4 choose 2 ways of doing that. So that means that if we're going to choose 2 that are defective, and again, if we're going to pick 4 of these transistors total, then that means that we must have 2 transistors that are good. So that means that we have 4 bad ones, so that means we have 20 good ones. So out of the 20 good ones, we need to pick 2 of them, and order doesn't matter, so there's 20 choose 2 ways of doing that. All this is going to now be over 24 choose 4. So that's the setup. So again, we can easily compute this by going 4 math PBR 3 4 choose 2 times 20 math PBR 4 choose 2 close divided by open bracket 24 math PRB, I should be saying, menu option 3, so 24 choose 4. Alright, so we can compute that, and notice our probability here is 0.1073. Now to compute the probability that none of them are defective, then again all that means is we're going to pick all 4 good ones. So again, we have to ask ourselves, how many good transistors are there in the box? We know that there are 20 of them. How many of them are going to be good? 4. Does order matter? Well, we want any 4 from our pool of 20, so order is not going to matter. So 20 choose 4 divided by all possible pickings. Well, there's a total of 24 pickings, and we want to pick 4. So 20 choose 4 divided by 24 choose 4. So again, we can compute this. 20 math PRB, menu option 3. So 20 choose 4, close, divided by 24 math PRB, menu option 3, 4, close. Press enter. So we can see that this is going to be about 0.456. How about the probability that all are defective? Well, the probability that all are defective means that we're going to pick all 4 bad ones from the bad pool, if you will. So again, how many bad ones are there? Well, there are 4 bad ones. And how many do we want? We want all 4 of them. So 4 choose 4 divided by all possible outcomes. So that's 24 choose 4. So let's see. This is going to be 1 over 24 choose 4. So that's going to equal to 1 divided by 24 math PRB 3 4 close. Oops, I didn't get the PRB menu option 3 4 close, enter. So that's going to be really, really small too, so about 0.00001. And then finally, at least 1 defective. So again, we have to remember, what does it mean for at least 1 to be defective? Well, that means, let's see, 1 defective. So that's 1 defective and 3 good, or 2 defective, 2 good, or 3 defective, 3 defective, 1 good, or 4 defective, 0 good. All right, so using this combinatorial stuff, we can see that this is we're going to have to take a look at it this way, or we could take the complement of this, and notice that the complement that at least one defective is going to be that none are defective. So the probability that at least one is defective, well, we can do one is good, one is bad, three is good, and do all of this. Or note that this is just 1 minus the probability that none are defective. And I think this is a little easier to compute because this is going to be 1 minus, well, the probability that none are defective means that you chose all the good ones. And we know that there are 20 good ones, and we want to pick 4 of them, and order does not matter, divided by all possible outcomes, so that's 24, choose 4. So again, we can compute this as 1 minus 20 math PRB, choose 4, divided by 24 math PRB, number 3, 4. Close. Enter. So the probability is going to be 0.5440. So when you take a look at something like at least one defective, and if you've got a lot that you have to compute, then you may want to consider complementary probability. So that's the trick on that one. So let's take a look at just one more. I think on this one I'm just going to do the setup and not do the calculator part for this one. Just setting these up, I think that's 95% of the battle. I've just showed you how to enter these into the calculator. So let's take a look. A parent-teacher committee consists of 4 people, is to be formed from 20 parents and 25 teachers. Find the probability that the committee will consist of these people. So we want all, let's just go through one at a time. All teachers. So the probability that we have all teachers, well, how many teachers do we have? We have 5 teachers. Okay, and what's the size of the committee? Is 4. Does it matter how we get these teachers? No, we're not filling any specific slots. Divided by all possible outcomes. Well, what's the total number pool of people that we have? Well, we have 20 parents and we have 5 teachers, so we have a grand total of 25 people in our pool, and we want to choose 4 of them. So the probability that we select all teachers, 5 choose 4, divided by 25 choose 4. So for B, we want 2 teachers and 2 parents. So again, we have to come back and ask ourselves, how many teachers do we have? 5 teachers. How many do we want? 2 of them. Does order matter? No. We just want any 2 teachers, so there's 5 choose 2 ways to do that. 2 parents. How many parents do we have? 20. How many do we want? 2. Does it matter how we get them? No. So order does not matter. So there is 20 choose 2 ways to do that. Divided by all possible outcomes. So again, the pool of people is 25. So there's 25 choose 4 ways to do that. So part C, all parents. Well, how many parents do we have? 20. How many do we want? 4. Does it matter how we get them? No. So there's 20 choose 4 ways of doing that. Out of all possible outcomes, so 25 choose 4. And then finally, 1 teacher, 3 parents, Hopefully by now we get the idea. There is 5 choose one ways of picking the parents, or I'm sorry, the teachers, and there is 20 choose 3 ways of picking the parents over 20 choose 4, I'm sorry, 25 choose 4 ways of doing that. Alright, so that concludes my video tutorial, and I hope you find this to assist you while computing your combinatorics, your permutations, and your probabilities.